Take it away.
Yeah. Hi, everyone. My name is Ziao. Today, I'm going to present our work, Noisy Computing of the Threshold Function. My co-authors are Nadim from U of Toronto, Banghua from U of Washington, and my PhD supervisor, Lele from UBC. And to begin with, let me use an example to motivate what we study. So in this example, we have n binary signals, x1 through xn, and we have n sensors that can make noisy measurements of them. So in a particular scenario, let's say each xi represents the indicator of the whether the ith device in a big system is functioning. And to carry out certain tasks, we need at least k of them are working. So to decide whether we can run this task, we essentially want to compute the threshold function, which is the indicator of whether the weight of this sequence is at least k. And now we have a centralized controller which can adaptively query one of the sensors at a time. So now the question is, how many cores do we need to compute this function reliably? So motivated by this, our problem is defined as follows. So let x be a binary sequence, and the threshold k function is simply the indicator of whether the weight of the sequence is at least k. So as a quick note, when k is 1, this is just the OR function. And when k is n over 2, this is the majority function. And our goal is to find an estimate of this function using noisy bit readings. So more specifically, at each iteration, we are allowed to submit an index as our query, and as the response, we get the value of this bit, but corrupted by some Bernoulli P noise. And after a total of m queries, we want to find an estimate of the threshold function. So now the question is, how many queries do we need so that we can achieve an error probability of delta for any input instances? So in the literature, this problem has been studied mostly under the special case of k equals to 1. So in those early works on logical circuits, they implies that for non-adaptive query strategies to achieve a vanishing error, the minimum number of queries is in this regime here. And the adaptive query strategies has been studied in this work by Fege et al. back in 1994. It has been found that the optimal query complexity is in the order of n log 1 of delta. So in some sense, this is already optimal. However, we know that the theta notation here still hides a constant. So in one of our previous work, we went beyond this order and figured out the exact constant in this bounds for computing the OR function. However, for the general k, the best known understanding is that the optimal order is in this order n times log k over delta. So we ask the same question. Can we find the optimal constant? So in this work, we take one step towards finding out this optimal constant. So our result can be summarized into this theorem here. So let's suppose k is less than n over 2, and this targeting error probability is little of 1. We show that to compute this threshold function, the optimal query complexity, the expectation, satisfies this upper and lower bound. So here, we are saying that we are restricting k is less than n over 2. However, some symmetry tells us that computing the threshold k is the same as computing threshold n minus k plus 1. So assuming this is not really losing any generality. And next, let me point you to the gap between our bounds, which is shown here. This tells us that when k is small, is little of n, then our bounds are essentially tight. We get the optimal constant. However, for general k, there's still a constant gap between our bounds. So the max of this bound is at value 2 when k equals to n over 2. So in the rest of my talk today, I will mostly talking about how we get this lower bound. So to show this, we essentially want to show that for any query strategy with queries less than this number, the error probability is at least delta. So the challenge here is always that we need to deal with an arbitrary query strategy with arbitrary adaptivity and arbitrary randomness even. So to tackle this challenge, we actually use some idea from the existing work by Fege et al. So the idea is that we want to transform any query strategy into a standardized two-step process. It has two properties. Firstly, it's an enhancement of the original query strategy in the sense that it gets more information on every bit. So it now suffices to analyze this enhanced version. And most importantly, the statistics from this process is much more tractable, allowing us to perform the analysis. So the definition of this enhanced process is based on this fact here. So if our query strategy has this upper bound on the query complexity, then the number of bits in X that are queried for at least this alpha times is at most this quantity beta. This is simply because the product of this alpha and beta is exactly this. So based on this, the process is defined as follows. The first phase is called a non-adaptive phase, where we just query every bit for a total of alpha times. And the second phase is an adaptive phase, where we can, based on the statistics from the previous phase, and adaptively choose beta number of bits to noiselessly get their values. So to see whether we say this is the enhanced version, we see that in the original query strategy, we have beta bits that are queried for more than alpha times. But now we noiselessly get their values. And for the rest of bits, they are queried for less than alpha times in the original query strategy. But now we query them for alpha time for each of them. So now it suffices to consider this enhanced version. So to analyze this, let's first look at the non-adaptive phase, where we query each bit for this alpha times. And we are going to view this through a balls and beans model, where we view each bit as a ball with some unknown weight. A bit with value 1 is a heavy ball, and a bit with value 0 is a light ball. And each query can be viewed as a noisy measurement of the weight that can return either light or heavy. And to capture the statistics, we are going to create alpha plus 1 bins with indices from 0 all the way to alpha. So let's say for this x1, exactly 1 minus p times alpha queries returns heavy, then we put it into this bin. And for 0, if p times alpha returns heavy, we put it into this bin. So we do this to every bit and get this histogram. So from here, we can see that the light balls are mostly concentrated around this region. So this is because each query is run with probability p. So the indices of each light ball is a Bernoulli with parameters alpha and p. So they mostly concentrate in this range here. And meanwhile, those heavy balls inside can be viewed as some outliers. So an important property we show for this step is some anti-concentration property. We show that for each of these typical bins for the light ball, it contains an outlier with this, at least this probability here. And we will see very soon that this is the key in showing the failure of this algorithm here. And one more thing I want to emphasize here is that from the query strategist point of view, we actually cannot observe all those weights, but instead we can only see the volumes of each bin. And this is all we get from this non-adaptive phase. So now let's look at the adaptive phase. So for this phase, we actually use some somewhat standard technique, where we assume there's some genie that provides us with some free information. And this is defined through a random process. And here we demonstrate this process using a marginal case of the threshold function, where there are in total k bits of value 1. So in this process, the genie first chooses a bin from this typical bin for the light balls with probability proportional to the volume. And then there are two cases. So first is shown here. This bin contains no outliers. In this case, the genie will just reveal all the information to us, which is saying it tells us all the indices of the heavy balls. And with this information, our algorithm can directly conclude the threshold function has value 1 without any error. And in just the other case, if the chosen bin contains such an outlier, then the genie will intentionally hide it from us. But to do this, it will reveal all the other k-1 heavy balls to us. And from our point of view, it's still not sure what is the value of this threshold function. And let's suppose this is what we observe. And there are two possibilities that lead to this. One is that indeed this typical bins for the light balls contains no outlier. This corresponds to the underlying truth of 0 for the threshold function. The other one is that there is an outlier hidden by the genie. This corresponds to the case of the threshold function equals to 1. So we essentially want to differentiate these two in this case. So to show the failure of this step, we need two very important facts. The first one is saying that each ball in this range is equally likely to be a heavy one hidden by the genie. This is implied by the process of how the genie chooses the bin. It is proportional to the volume, and this introduces some level of symmetry among these balls. And this implies that no matter how we design the adaptivity in this step, they are just equivalent as arbitrarily choose beta balls to reveal their weights here. And the second fact is that the total number of balls in these typical bins, we can bound it to be at least n minus k minus little of n. So from here, we have in total this number of balls here, but we only have a beta budget of revealing. This tells us that at least there's a fraction of epsilon balls that are not revealed. And if the ball hidden by the genie is exactly in this fraction, then this will cause a failure of this query strategy. And putting this with the fact that the genie will indeed hide a heavy ball from us with probability little omega of delta, then this tells us that give us a lower bound for the error delta for this enhanced query strategy. And this shows our lower bound. And finally, to conclude my talk, in our work, we provide new upper and lower bound for the optimal query complexity for computing the threshold function. So these bounds are tight in the case of k is little of n, but there's still a constant gap of at most 2 for general k. So a natural question is, how can we close this gap? So in fact, this problem have been very recently solved. So in a work that was just posted on arXiv earlier this month by Gu, Li, and Xu, they show the optimal bounds for any choice of k. So by comparing their bound and ours, we can see that actually our upper bound is tight, while our lower bound is not. So in their new work, they actually use some technique to reduce this problem in the case of large k into the case of k equal to little of n. And by doing this, they can extend our tight result into any general k. And finally, there are still many open problems. So firstly, in all this line of work, we're always assuming that this noise level p is bounded away from 0.5. And also, we are always requiring this delta is going to 0. So a natural question is, how can we extend this type of result to those cases? And also, is it possible to extend this type of result, this type of tight result to some larger family of Boolean functions? And that's all for my talk. Thank you very much.
Thanks. Questions? One over there.
Hey, thank you for the talk. I guess I'm completely not familiar with the field, so could you maybe just quickly tell, why does knowing the constant matter in this case?
Oh, actually, knowing you mean the knowledge of p, right?
But generally, you're trying to find the constant on this. Is there like a real-world application where actually knowing the constant changes what people do?
So in fact, so for the existing result that knows the constant, so actually we put in this in the paper, but not in the slides. So we do some numerical experiments for some particular choice of like k, delta, and n. So in the existing bound, like the constant gap is something like a few thousand, something like that. So I would say that's still like some large gap, especially for finite n. So, but now we can exactly get this constant. I think this is some improvement, I think.
Thank you.
I'm curious, yeah, this is a nice lower bound framework and technique. I'm just curious, how, is this like the only type of framework, or are they sort of different? Because there's at least your work, there's this work by Gu et al., and then there was a previous work which had done it for k equals 1 and like n. I'm just curious, how much diversity is there in terms of lower bound techniques, or are they sort of the same recipe?
So, okay, if we compare this work and our previous work, the lower bound technique is totally different. So in our previous for the OR, so basically we are using something called the LeCam's two-point method.
Yeah.
So just using that method, you directly get that bound. And actually this applies for any constant k. But when k becomes growing, that will just fail to give the type. Actually, it won't even match the order, I think. But using this type of technique, we are able to get this type of bounds. And in Gu's work, so they are basically extending our result from k is little of n to general k. So that's somewhat problem reduction techniques. It's very different from this.
Oh, I see. They just reduce to the known cases, basically.
Yeah.
Cool. Anyone else want to ask?
Yeah, right.
And did you consider like asking a batch of users
like asking a binary function of sum of the bits. Yeah. Oh.
Asking like a group of H users and asking them whether the fraction of users among them, which are one, is higher than H over K.
Yeah, we haven't considered like that, like those kind of cores. Maybe we can discuss more about this. I think this is.
Make me feel of like the setting your setting is make me feel like local differential privacy. It's like quite things. No?
Oh, differential privacy.
Yes.
Yeah, actually.
Before responding to you, each user privatize their response, and then you aggregate them. But if you consider like more like a central file, more like a central setting.
Yeah, I think maybe I'm not very familiar with that. Maybe we can discuss later more. Yeah.
Anyway, thanks a lot. Nice talk.